All right, we're recording. So today I'm going to talk about accelerated motion. Okay, so we talked about the idea of acceleration, but we never found the displacement. If you have acceleration, we never found the final velocities and all that stuff. So we did some of it graphically, but now we're going to see if we can come up with some equations that we can use when we do the math, because so up to this point we haven't done any math. All right, so the first thing I'm going to do, I'm going to start with a velocity time graph. Actually, let me just write the equations that we're going to be using, and we'll do a little proof to these equations. Then the next one is Vf equals Vi plus At. Now Vi, I stands for initial and F stands for final. Delta X, that's your displacement. That's not your position, that's displacement, which means this can be also written as X final minus X initial, or XO. The next one would be delta X equals VIT plus half AT squared. And the last one does not have time in it. And we're going to do a little proof to how we got this equation, where they come from. So I'm going to do a VT graph with a constant acceleration, because the slope gives you the acceleration here. So I'm going to say this is the initial velocity. This point here is the final velocity. And I went from Vi to Vf in a period of time t. So if you recall, to find the displacement, we just took the area and the velocity time graph. So if I do the area here, if I turn this around, if I look at it sideways, that looks like it's a trapezoid. So the area of a trapezoid, which is, this is delta x. If I do this area, I get my displacement. I don't get position. Delta x equals, the area of a trapezoid is you add up the two bases, cut them in half, and multiply by the height. And the height of this trapezoid is this distance here. So the bases are this much, which is Vi, and this much, which that value is Vf. So the first one was pretty easy. All right, let's look at the second one. Second one should also be easy too, because we defined acceleration as change in velocity over time, which is equal to the final velocity minus the initial velocity over time. So if you just play with this equation, if you manipulate this equation a little bit, if you look at this part here and this part, if you move the t here and you add Vi, you end up with the second one. So we're good with the first two. Let's do the third one here. No, the third one I'm gonna, all right, so for the third one, I'm gonna write, I'm gonna write this equation here, but I'm gonna substitute the time from the second equation. Okay, so I'm gonna write the first one, but instead of writing t in here, I'm going to write t as being Vf minus Vi over A. Actually, I think I just did the fourth one, but I'll come back and do the third one. So delta X equals, this is going to be 2A at the bottom. And if you pay attention to the top, it looks like that's going to give us a difference of squares. So in other words, if I move the Vf here and the Vi here, this is like A plus B times A minus B. So that should be Vf squared minus Vi squared. And if you just manipulate that a little bit, you multiply everything by 2A, you get 2A delta X. If you move the Vi over to this side, you end up with this equation. So let's see how we can come up with the last one. I mean, the third one. All right. You know what? This is what we're going to do. I'll leave Vi here, but I take this Vf and I replace it with Vi plus At. Then there is a t on the outside. Yeah, that's what it was. All right. So this is 2 Vi, and delta X equals, now if you divide both sides by 2, we should get Vi, and same time we multiply the t, plus 1/2 A. Now I'm pushing this half inside here and pushing the t inside also. 1/2 A t squared. And those are the equations we're going to be using.